We're continuing our discussion of the one-dimensional harmonic oscillator. In part A, we showed that this is a solution of the Schrödinger's equation for n equals 1 state in corresponding energy 3 over 2 h bar omega. Part B asks us to find the normalization constant A1. Now, the probability density is absolute value of psi1 of x squared, which is a1 squared x squared e to the minus alpha squared x squared. The function itself was e to the minus alpha squared x squared over 2, so we're taking its square. And the statement that the particle exists somewhere is in the integral from minus infinity to plus infinity, probability density function dx is equal to 1. That's the statement of existence. So that's a1 square integral from minus infinity to plus infinity x square e to the minus alpha square x square dx, and this must be equal to 1. So we have to perform this integral. Okay, now the first observation is that I have square and square here. This integrand is even function, which means f of minus x is equal to f of x. So first I make this observation that the integrand is an even function. Therefore, the integral from minus infinity to plus infinity must be equal to twice the integral from 0 to infinity x square e to the minus alpha square x square, and this must be equal to 1. Now what is this integral from 0 to infinity x square e to the minus alpha square x square dx? Now we can recall that the integrals of the form from 0 to infinity e to the minus alpha x square x to the n dx have this recursive solution, and particularly for n is equal to 2 we have integral 0 to infinity e to the minus alpha x squared dx. That's 2 minus 1 over 2 alpha, which is 1 over 2 alpha integral 0. For 0, we have integral 0 to infinity e to the minus alpha x squared dx, which is 1 over 2 square root pi over alpha, and this is 1 over 4 alpha square root pi over alpha. Now, this is shown in great detail in this link here. I have done it before in Physics 221 class lectures. I will also put the link for the description of this video. Okay, so applying this result here, we have 1 over 4 alpha square root pi over alpha for e to the minus alpha x squared dx. I have here alpha square, so instead of alpha here, I'm going to put alpha square. So with that, I have the result 1 over 4 alpha square square root pi over alpha. Okay, so I'm just applying this result here, substituting alpha square. Okay, so if this is going to be substituted into this, I will obtain normalization constant A1 is equal to 4 alpha cube divided by 2 square root pi. So remember, I have 2a1 squared times this equals to 1. So 4 alpha cubed divided by 2 square root pi is a1 squared. So a1 is this to the power 1/2. That's the square root. So this is going to give me, first of all, I noticed that this 2 will get rid of this 4, make it 2. I have 2 divided by square root pi, and then I have alpha cubed. Remember, alpha is mw over h bar, mw over h bar to the power 3 over 2. So let's remember, alpha square is mw over h bar, so alpha is mw over h bar to the power 1/2. I take the third power, mw over h bar to the 3/2. So that's what's inside the parentheses, and this should be to the power 1/2. So that will give me 2 to the power 1/2 divided by pi to the power 1 over 4 mw over h bar to the power 3 over 4. So I have my final answer for the normalization constant. So a1 is equal to 4 over pi, I can write it this way, to the power 1 over 4. This is 2 to the 2 divided by 1 over 4, which is 2 to 1/2. And then I have mw over h bar to the power 3 over 4. That's the normalization constant we're looking for. Part C, show that the probability density has a minimum at x equals 0 and maxima at x equals plus minus 1 over alpha, corresponding to the classical turning points for the ground state n equals to 0. Okay, so I just realized that n equals to 1 is not the ground state. So this is the first excited state here. So this is a solution to the first excited state in part A, which apparently has x equals to 0 because we're going to get this solution. All right, so for part C, the probability density is now a1 square x square exponential minus alpha square x square. And if I take the derivative of the probability density function with respect to x, I can find the extremum points. So the first term is 2a1 square x times exponential. So 2a1 square x times the exponential. And then the second term is minus 2 alpha square x multiplied with x will give me minus 2 a1 square alpha square x cubed times the exponential. This is equal to 0 at the extremum points. So this is basically x times the exponential term. And here I have 2a1 squares disappearing. So if I put it in x times exponential parentheses, I will get 1 minus alpha square x square. 1 minus alpha square x square is equal to 0. So this has solutions if x is equal to 0 or 1 is equal to alpha square x square, which means x is equal to plus or minus 1 over alpha square root. One over alpha square root. These are the extremum points for the probability density function. Now, if I substitute x is equal to 0 into the probability density function, I will get 0. If I substitute x is equal to plus or minus 1 over square root alpha into the probability density function, I will get a1 square x square with basically 1 over alpha exponential minus alpha square, it was minus alpha square x square minus alpha square over alpha is what I will get. And this will be equal to a1 square over alpha e to the minus alpha. So this is a positive quantity, this is 0, therefore I conclude that this is the minimum and this must be the maximum. All right. So I'm realizing that probability of x is equal to 0 is less than probability at x is equal to plus or minus 1 over square root alpha. Okay, so indeed we have shown that x equals to 0 is a minimum and x is equal to plus or minus 1 over square root alpha. The turning points are corresponding to the maximum probability. We can also check the second derivative of the probability density function with respect to x, and this is going to give us 2a1 square times the exponential plus 4a1 square alpha square x square times the exponential minus 6a1 square alpha square x square times the exponential and then minus 4a1 square alpha square x to the fourth power times the exponential. And we check what happens at x is equal to 0. At x is equal to 0, all of these terms will disappear and we will get 2a1 square. 2a1 square is positive, so it has a positive curvature, therefore x equals to 0 is a minimum. Okay, so we find that x equals to 0 is a minimum in the probability and x is equal to plus or minus 1 over square root alpha, the turning points, 1 over square root alpha is a maximum. All right. So in this part of the problem, we have solved for the normalization constant by looking at the existence condition minus infinity to plus infinity probability dx, the fact that the harmonic oscillator exists here is equal to 1. So this is going to give us, by performing this integral, the normalization constant. Then I recall the integrals of the Gaussian using these from a previous lecture, which is linked here, and I can use that result to find A1. Now in part C, I have this probability density function. I take its derivative with respect to x to find the extremum points. Extremum points are x equals 0 and x equals plus or minus 1 over square root alpha. I can find which one is minimum, which one is maximum by direct substitution. So that's what I did here. Or I can take the derivative, second derivative at x equals to 0, and I can see that that's a positive quantity, which means there's positive curvature in this extremum point. That means it's a minimum. So x equals to 0 is a minimum, and plus or minus 1 over square root alpha is a maximum.